It's my great pleasure to introduce Professor Shamir Shende, who has helped develop the TAU performance system and as well as the program database toolkit, PDT, as well as being involved in the extreme scale scientific software stack and the HPC Linux distro development. Samir's research interests include tools and techniques for performance instrumentation, measurements, analysis, runtime systems, HPC container runtimes, and compiler optimization. He is a research professor and the director of the Performance Research Laboratory at the University of Oregon, and as the president and director of the Paratools company, he and Paratools USA and France. He is providing this training session to us today on the TAU performance analysis tools and E4S. Samir, it's a great pleasure to have you here in Perth. We met a couple of times during some of the conferences, and you know some of the Pawsey stuff. So it's a great pleasure to finally have you here and host you here for this two-day session. So thank you so much for being here.
Thank you very much for inviting me. It's a great pleasure to be here in Perth. And today I will describe the TAU performance system and the extreme scale scientific software stack. And we'll do a lot of hands-on sessions. Please feel free to stop me and ask questions. It's a small group relatively, including our participants online. And please feel free to ask questions and unmute yourself online as well. The rough schedule that we are going to follow today is that we'll have a short break in the morning and afternoon, and we may have the second break at the end, trying to end at around 3:30 p.m. And today we'll look at how to use these tools in depth on AWS, and tomorrow we'll look at the Cetonix system and look at how we can evaluate the performance of our codes running on GPUs and CPUs and different runtimes. I'll cover how to use TAU with MPI applications using TAU. We'll look at OpenMP. We'll look at the OpenMP tools interface. We'll look at CUDA with support for NVIDIA GPUs online on AWS. Tomorrow we'll look at ROCm and look at the AMD runtimes. We'll look at how we can assemble an entire software stack and use this effectively. So there's quite a bit of material here, but you'll notice that in most cases, you don't need to modify your applications in any way. You just have to launch them in a separate way and then evaluate the performance of your codes and run the analysis tools. So as some of you may have already signed on to AWS, these are the steps. We'll go to the e4s.io/tutorial and grab an instance, and then you just launch this instance, access this instance through the web browser using one of these instances. Like if I reserved an instance called tut009, then I'll go to tut009.supercontainers.org:8443. That's the DCV port /#E4S, and give the login as tutorial and password as HPC Linux 12!! If you want to leave, just kill the browser window. Don't exit from the instance. So just kill your browser if you want to exit, and you can again get back on, and the state is preserved. These are instances that are currently running in Oregon, but you'll see that they are they have very low latency of access, and you should be able to use them well. All the graphics are rendered remotely, and I'll show you an example of how to use these. And tomorrow, we will look at Cetonix, and we will use the remote viz.pawsey.org.au system with FastX. And there we will launch the application like an extern over here, and then we'll download the FastX client running on your laptop. You can also do this through the web browser, but in FastX it may be convenient to do that, especially the copy-paste operations and such. And then we will grab a node and SSH to Cetonix, and then from there we will be able to run the web browser through the web browser or through the FastX or GUI tools. In most cases, you can just download a demo PK file just to verify that it's working well and launch Prof, the GUI tool that we will use today, and see the 3D visualization window like this. Now, many of you are probably wondering, how do I use TAU? And so this is a quick start guide for Cetonix, where you can allocate a node using the slog command at the top. Just do a module use command to point to these module files directory, and then just load the TAU module. When TAU is loaded, you have TAU_exec as a tool in your path. And if you run your application with MPI or with srun or MPI run, you can just launch it with TAU exec with the -EBS or event-based sampling flag and generate the performance data. And I'll show you some instances where we can use all three different compilers. It is the GNU compilers on Cetonix, or the Cray compilers, the progenv Cray, or the progenv AOCC with the AMD compilers, and then generate the performance data by just launching the application with this TAU exec tool. So if there is one thing you take away from this training, it is that you don't need to modify your source code. You don't need to modify your build system or even your application binary in any way. You just simply launch the application using a tool called TAU exec with some flags, and we'll see what those flags are. But with just that simple TAU exec, you should be able to generate the performance data in profiles, in traces, and there are many flags that can affect what you generate, and we will look at all that. But the simple takeaway is you can just start with an MPI application, just launch it with a TAU exec-EBS after loading the TAU module, and generate the data, and then launch our visualizers to view what the performance data contains. So is that okay? And there are some cases of what you would like to use, whether it is with ROCm, without ROCm, with pthreads, GPUs, and such. And so there are various flags. For analysis, we have tools like pprof, which is a text-based tool, and Prof, which is the GUI. And we'll launch these either locally on our laptops or through the web browser for AWS instances, or even through FastX with a remote visualization. So this is the quick start guide. It tells you what we are going to do, how we are going to generate the data for profiling, how we do it for tracing. And there are many tools for analysis of trace files, including Vampire, and we have a Vampire license included in the AWS instance. So you can just launch with Vampire. And then Perfecto.dev is a Google tool, which is a very versatile tool for visualizing traces. TAU can generate traces that can be visualized there. And then you can also use JumpShot, which is supplied with TAU. If you want to install TAU on your laptops, it's very easy. Just make sure you have Java installed. And we have Java binaries here for Windows or Mac, both x86 as well as ARM64 Macs, or on Linux. And just follow these instructions to install if you want to install it on your own laptop. So with this, you have already had a look at the AWS instances. I hope many of you are already able to log in and grab a node, and we have made it simple so that you don't need to install anything. You just need a web browser to be able to access the AWS remote desktop, and everything is installed for you, and you have a remote desktop session, which includes a GPU. And so you have, I think, eight cores on this instance, Xeon cores, and a GPU on AWS. And we look at all the different options that are available. But let me just first say that that TAU is a comprehensive profiling and tracing toolkit. I've been working on it since 1994. And it has a long history. It has an integrated performance toolkit which has support for adding hooks to your code transparently, so you don't need to modify anything. It has measurement options. It has a range of options for generating different types of performance measurements. Some people call it the Swiss Army knife of performance evaluation tools because it does a lot in terms of support for different platforms and different measurement options. And it has some mature visualization tools as well that we will use. It's widely ported. Our goal is to make sure that it's available on all the HPC platforms. And it comes with a BSD style open source license. It's very easy to integrate it with your application frameworks. You can use it with a number of different MPI implementations. And you can learn more about it on our tau.uoregon.edu URL. So as far as our goals today are concerned, in this tutorial, I would like you to have a better understanding of the key concepts of performance evaluation tools so that you can apply these concepts to not just TAU, but a number of other tools. When you look at some performance data, you can reason about it, say, how did this get generated? What is it trying to show me? What is the performance model? And learn about these concepts. You should learn how to collect and analyze data from hardware performance counters, how to instrument your programs using TAU, which are the different measurement options, environment variables, how to use the TAU profile browser, and a general familiarity with TAU for different types of languages. Now, I assume that a number of our participants here are interested in MPI in particular. Is that right? MPI with different runtimes, whether it is pthreads or Cocos or CUDA or ROCm or OpenMP, but different MPI with different node level programming models. And TAU supports all of those. And we'll also see how to use TAU with the extreme scale scientific software stack, the E4S, which provides the instances that we are using for the tutorial. So a number of you have already used tools before, and this is the optimization cycle. What we do is we add hooks to our codes. We have all done this, right? You may have used get time of day. You have a loop, and you add a hook at the beginning of the loop. You say T1 equals get time of day. There's a for loop. At the end of it, you put T2 equals get time of day, and then you have a print statement that says the time spent in the loop is T2 minus T1, right? We've all done this to measure the performance of our loops in our codes. And those approaches don't scale very well when you suddenly run the same code on 256 cores and you try to do something with an MPI reduce operation. You try to get all the data, you try to get one single number, and it becomes cumbersome. So instead, you can leave aside those DIY approaches and look at the performance evaluation tools where you can expose the different factors. Ask yourself, what are the key actions in my program that are relevant? How do I observe those actions encoded as events when the application is running? You launch an application, let's say you launch an application on 4 CPUs. It's running with MPI. You want to observe what's happening in that code, you want to understand where is it spending its time? Where is it spending its resources? Does it talk to the GPU? How often? What kernels are running on the GPU? What is running on the CPU? How much time does it spend in the data transfer between these two? So you want to observe these factors. You need to add hooks to do that. And that's the first step, the instrumentation. Once those hooks are in there, you generate a profile which shows you how much time was spent in different threads of execution on different parts. Then you analyze, you say, okay, I understand that it's taking a lot of time in this MPI barrier. How can I deal with that? You create a hypothesis. You say, do I really need this MPI barrier? What if I just get rid of it? And then, based on that, you look at the profile, you create a hypothesis, you optimize the code, and then you are able to redo the entire optimization cycle until you are satisfied. So with TAU, you can expose these key actions that characterize your application as events. So in general, there is some location where an event takes place. It could be inside a function. So you say, at the entry of a function, this event takes place. At the exit of this function, this event takes place. There's a start and stop. There's a timer associated with the start and stop actions. Now that, adding a hook to your runtime, whether it is in the MPI library or in your code, is a direct instrumentation. And the observation is considered direct if that instrumentation or probe is inserted in your code, and then you make some measurements and associate it with some context. We also have support for indirect instrumentation. With indirect methods, you just interrupt the code. How do you interrupt the code? It could be through a timer, a periodic timer. Every 30 milliseconds, the program gets interrupted. When it gets interrupted, you can observe the program counter. You can see how many samples are collected. And then based on that, you can infer the performance. You can say that the program was spending so much time in this code region. So based on this, you can have event-based sampling. So wherever you see the words EBS, it stands for event-based sampling. And you can interrupt the program periodically. Now, once you insert hooks in your code, you can generate inclusive and exclusive time. How do I do that? Well, if there is a function, say foo, let's say it takes 100 seconds, and it calls another function called bar. And if I insert hooks at the entry and exit of both foo and bar, then I can say that the green region here is the inclusive time. Let's say it's 100 seconds. And if bar takes, say, 30 seconds, then you can say this orange region is 70 seconds, or the time spent exclusively in the function foo. Okay, so you can subtract the contribution of the child function from the parent and say, with direct instrumentation, I can record and precisely tell you the exclusive and inclusive time spent in that routine. And you will see this in the TAU profile. You may see a top-level .TAU application, high-level timer, and then you may see the time spent in different code regions. And this is the exclusive time, which shows you the time spent in key functions and loops. So there is the difference. You want to see the exclusive time spent in your code. You say, where is it spending most of its time? Show me the top 10 routines, the top 10 code regions that I should focus my attention on. And you can get that with code instrumentation. Now, in case you're wondering, what can I see? What performance data can TAU provide to me to help me understand the performance of my code? It can show you how much time is being spent in your different code regions. These code regions may be functions, they may be loops, they may be individual statements. So yes, we can look at the performance data right down to the statement and see how much time is being spent. We can see what's happening on the GPUs, the time spent in individual kernels executing on the GPUs. We can look at the data transfer between the CPU and the device. Yes, you have a question? No, okay. You can, instead of time, replace it with hardware performance counters. These are low-level counters available on the microprocessor that can show you low-level data such as the number of cache misses, the number of instructions executed, the number of instructions where your process was stalled waiting for resources. So you can get low-level statistics right down to the statement level. You can see how much time your application spent waiting in an implicit barrier in an MPI collective operation. Now, I'm sure you've used MPI collective operations in your code. You have MPI bcast to send data to all the ranks. You have used MPI reduce. You have used MPI scan, gather, all of these application level routines. But in each of these routines, MPI is waiting for all the members of that communicator to enter that operation before it can proceed. Some tasks enter right away, and some others are doing other things and they enter late. So there is a barrier in all of those collective operations. You want to know how much time did I waste at that barrier inside the collective operations, and what did it cost me in terms of which MPI operation was performing this. And you don't need to generate traces like some other tools where you generate the full trace file and then you see all the timestamps and then you go and analyze that and generate a total amount of data. You can do that online with runtime summarization, with profiling in TAU. And it can show you this is the amount of time you wasted in an MPI collective operation, which was called along this edge of a call graph. So you can identify where your program is wasting its resources simply by looking at the total time spent in a collective sync operation. And we look at that. You can see the memory usage of your code. You may be wondering, how much memory does my MPI application take? What was the max value? And by memory, I mean the sum total of the stack, the heap, the data, the text, the BSS, the total amount of actual RAM usage in my code as it runs the application. What was the high water mark of that memory usage? What is the max value? Suppose your application reached a value of 2 GB in one MPI rank, and you say, I have 16 MPI ranks on that particular node. So you can say that the max value I'll ever need is about 32 GB on that particular node. It may be less, because not everyone may reach the max value at the same time. But that's a just back of the envelope calculation. So you can see what is the max value, the memory footprint of my usage. You can see the I/O characteristics of your code. Now this is interesting because I/O is becoming more and more important for all of us. And whether it is through third-party libraries like ADOS2, HDF5, or POSIX I/O directly, or MPI I/O, you want to track. You want to track and find out which files did my application touch, on which file systems. What was the amount of data that passed through the read and write calls? What was the read bandwidth? What was the write bandwidth? What was the extent of variation of those? And see the overall picture of I/O in your code. You may want to see what is the contribution of each phase in your application too. And by phase, I mean you can just look at the output of your code, and you'll see the different phases emerge from that. You might see an initialization phase, you might see a data distribution phase, you might see a solver phase, you may be doing some meshing, you may have print statements that describe what's going on in your code, and those are all relevant phases. And you may want to see a phase profile that shows you not just the time spent in MPI bcast in the whole application, but MPI bcast when it was in the solver phase. So you can create a phase-based profile with TAU. It can show you what's happening in the code. You can even see how the application scales. What is the efficiency? What is the runtime breakdown of performance across the different core counts? So it can show you a number of these parameters, and we'll see how we enable all that collection by TAU. Now, there are 3 distinct modules in any performance evaluation tool, not just TAU. The first module has to do with inserting the hooks in your code, the instrumentation. Now, as you look at different tools, you may see that there are ways to insert hooks directly in the source code through the compiler, at the MPI level, library level, or just launch the binary or even edit the binary. TAU supports all of those modes. Today, we will focus on using TAU in the most minimally intrusive way, which is just using the binary. Then once you have the hooks in there, you have to perform the measurement, the profiling, the tracing, and different modes of profiling. And once you generate the data, you can analyze it using tools like Prof and Vampire. TAU supports a number of different languages and also runtime systems. Is there any interest in Python or Python? Yes. How about Fortran? Is that of interest? There is, right? A lot of interest in Fortran. Okay, good. And how about emerging languages like, I shouldn't call them emerging anymore, Chapel? Is there interest in anybody looking at Chapel at all?
I haven't heard of anyone using it on our systems.
And Julia.
Yeah, something that right now it's just a couple of projects, but yeah, we've seen some rise in Julia.
Very interesting you mentioned Julia, because we have support for Julia in E4S, and you have a container where Julia is installed with support for MPI as well as with support for the GPU runtimes in E4S. So that is of a lot of interest to us as well. And yes?
Samir, with Julia, right now they don't provide official support for AMD GPUs, all right? I think there was an old project, but right now it's stalling. Do you know?
Support for AMD
Julia support for AMD.
So there is a AMD GPU.jl.
Okay.
And there is support, but it's evolving, as you can imagine. And with each new version, you'll find that it's getting better support. They do have a lot of support for CUDA. And we are, in our containers in E4S, we do support that. And as far as MPI, we have support for MPI, we have support for OpenMP with the OpenMP tools interface, where we can observe what's happening inside the OpenMP regions. And we have support for a number of different Cray runtimes, whether it's DMAP or Eugenie or OpenSHMEM and other SHMEM derivatives as well. And we have support for GPUs. And with GPUs, we are, as you can imagine, with the Department of Energy in the US supporting our development, we have support for Intel GPUs, as well as AMD, as well as NVIDIA GPUs. All 3 manufacturers are important. And we support CUDA, OpenCL, level 0 for Intel, ROCm, OpenACC, and we can generate profile data which can be visualized in Prof, Perf Explorer. We have a full database that we'll also look at, and the 3D profile browser. And we support both direct and indirect performance observation methods in TAU. What that means is that your runtime, whatever your runtime may be, can be instrumented with TAU. So you could start with an application that uses CUDA or ROCm or pthreads or OpenMP, and all of those calls can be inserted directly with TAU with no change to the binary, because those are standard interfaces. And then we can interrupt the program and generate detailed samples and identify what the rest of the code is doing. So it's a hybrid approach where you can have direct instrumentation that gives you accurate measurements for inclusive and exclusive time, and then indirect methods such as event-based sampling, and generates data that shows you what the application was doing in the rest of your code. Okay? And you can have both these interval events with begin and end, start and stop timer calls, and interrupt events where you have just number of samples collected. But how does this help us? It helps us generate this detailed exclusive and inclusive time breakdown in the application like this. And it can help us generate profiles as well as traces. Profiles can show you the total time spent in each application routine. So you could see that MPI barrier was called 100 times. The total time spent in the MPI barrier was 10% of your application, maybe 50 seconds. What I did here is we entered the MPI barrier and we exited it, and we had a timer. And we summed up that timer over the execution of your application. While traces show you when the events take place along a detailed timeline display. So you can see every entry and every exit in the MPI barrier call. And then you can see, based on which kind of profile you generate, the distribution, whether it is a flat profile, which just shows you how much time was spent in different code regions, or a call path profile that shows you who called which function along a calling sequence. And we can look at the full trace file and see the detailed data based on either direct instrumentation or indirect using sampling. This is how samples work. You get an interrupt periodically from the system timer, say every 30 microseconds, 30 milliseconds, and then based on the number of samples that you collect, you can assign that and say, I collected 100 samples, if say the sampling period was 1 second, and I had 30 samples collected at food.c in line number 12, then I can say 30% of the time was spent in that code region, and so 30 seconds were spent there, based on the number of samples. But notice that between T5 and T6, you can miss something that happens when the sample is not collected. But if your application is stuck in a barrier for 10 seconds, you can be sure that it will gather the samples over there. And for fine-grained instrumentation, you have start and stop timers, which can be inserted in the code or in the runtime system. And you can capture exactly what happens based on the entry and exit, so you don't miss out on any function. But then the flip side is that if there is a function that gets called frequently, and you instrument the entry and exit of that function, then it can sometimes perturb the total execution and dilate the runtime. We have support for throttling of events, where we just throttle away the function that is lightweight. Let's say it executes over 100,000 calls, and it takes less than 10 microseconds per call. You could say, this is trivial. I don't want to insert hooks in this. So you can speed it up right after that, and then you'll see the name throttled in the name of the function. So you know that you can ignore that data.
This is in case of recursive call functions, or?
No, it can be in iterative functions too. If you have a small function and you just call it in a loop 1 billion times and it's just taking 3 microseconds per call, then you may want to say, I don't want to perturb my application, just don't insert hooks in this at runtime. You can even re-instrument the code and weed out those lightweight functions in the next execution. So you can do that. And then generate flat profiles which collect the basic routine level data. You can collect the call path profiles which show you how much time was spent along a calling edge. So here you can see that when main called F1, when F1 called F2, when F2 called MPI send along this 4-node call path, it spent 30 seconds in that MPI send along this edge. You can set an environment variable called tau call path depth to get these values. You can also say tau call site equals 1 and generate a call site profile where you can see the time spent in that function at a given point in the code. So you could say MPI barrier at line number 12 in the function foo took so much time. At line number 15, it took so much time. So you can partition the time based on where it is called from. And you can have the full phase profile as well. Now we have support for many different runtimes. We have MPI, where we can support the PMPI interface, which shows you the total time spent in the MPI call. We also have support for this collective sync wait state identification. And I mentioned this because sometimes you want to find out how much time did my application waste in the MPI collective call. We also have support for the MPI tools interface, where we can see what's happening inside the MPI layer. And by that I mean, you may have a case where you may want to know what's going on inside the MPI. There is a network interface card. There is a queue, and packets are queuing up. Suppose you want to find out what is the length of that queue. Is it 10 packets queuing up to be flushed out? Is it 10,000 packets queuing up? Is it 10 million packets that are just stuck there before they can be flushed out of the network card, right? That information is only available inside the MPI layer. And MPI implementations can expose that using the MPI tools interface with the performance variables. You can also dial down or dial up MPI resources using the control variables. You may want to find out how much memory is my MPI using. Okay, I realize that I am at 99% of the total memory usage in my code, and it's going to crash any minute. Can I dial down the MPI resources that are not being used and free up the memory for my application? You can do that at runtime using the control variables. We capture the time spent in routines in the pthread interface, in the OpenMP interface using the OpenMP tools interface, in the level 0 interface from Intel. So you can see exactly how much time was spent in Intel GPUs in the kernels executing there. And these may be launched by the OpenMP target offload directives. Is anybody looking at the OpenMP target offload directives here? There is interest, right? So with the OpenMP tools interface, we can capture that information. And then we can see OpenACC events as well. I don't know about OpenACC. Is there interest in OpenACC over here?
Both
Yeah.
OpenACC and OpenMP main for Fortran codes.
For Fortran codes, yes, exactly. And so without any modification to your application, you can just launch it with tau exec and then gather that information for the OpenACC, where you can capture the actual data transfers between the host and the device on a per variable basis and say, when this variable was transferred over, how much time was taken. You can see OpenCL events. Is anybody using OpenCL on Cetonix or?
We actually have OpenCL training lined up also for, I believe June or May. So yeah, we are also looking at OpenCL. So OpenCL, Cocos, Rockham, of course, as well, and the directive-based programming models that you mentioned, so OpenMP and OpenACC, all in the context.
So this is a very good fit then, because we cover all of these models, including Cocos. And with Cocos, they have the first argument in every Cocos parallel for or parallel reduce call, where you can just insert your own user-defined text that describes what that is. And then that text can flow into TAU, and you can see detailed information, performance information at the Cocos level, or at the Python level, or the Rockham, or CUDA level. And we will look at all of these examples with maybe using CUDA profiling tools interface, tracking the data transfers between the host and the GPU, looking at rock profiler and rock tracer instrumentation on Cetonix, and using it with MPI, without MPI, with different progenvs, like with progenv Cray, progenv AOCC, progenv GNU, all of those are supported. And you can mix and match them with TAU. So you could say, I have a code which has MPI with OpenMP with target offload directives. How do I configure TAU to support both of those cases? Or I have support for Python with CUDA without MPI, or MPI with OpenCL, or Cocos with a different backend. So we have different ways to insert code in all of those cases. We have support for adding hooks to your program using source code instrumentation, using a tool called Program Database Toolkit, where we can recompile the code and add hooks to your code. We also have a filter file that can reduce the runtime overhead, and you can use this filter file or selective instrumentation file to target certain code regions. We have support for compiler-based instrumentation to add hooks. And we even have a plugin that can be used with LLVM-based compilers like HipCC that can say, instrument this, don't instrument that. And then don't instrument code that's going to the GPU, because we'll track it using Rockham, Rock Profiler, Rock Tracer. And then we have hooks that can be added through many of these other libraries. Many times if you have a large application, there's a good chance that that application lifetime is greater than the lifetime of your supercomputer, right? It has evolved organically over the past few decades. There is probably already a timing library inserted in the application. What that timing library is doing is that it has defined some key user-defined locations and some text that describes what the code is doing. In a PETC library, you may have something like SNES solve. Now that is very important to a PETC developer. When they look at the profile, they are saying how much time is spent in that particular solver internally, right? You have a number of these libraries, whether it's cam timers, perf stubs, Cocos, Prof. These are used extensively in your codes. What you can do is you can map those libraries directly to TAU calls, so that none of that instrumentation that's already in the code goes waste. We can access that, and we can generate TAU profiles that include those calls, because those are very valuable. They are giving the application developer key insights into the workings of their code. By mapping those calls into the TAU start and stop calls, you can see a very interesting profile with the minimal intrusion, which captures all the work that they have put into the adding of those hooks to their codes. I would love to talk to the developers here and find out, are there libraries like that that you are already using for starting and stopping some timer? I don't care which library you use, but we should be able to map that into the TAU calls and generate profile data in such a way that The application is still uninstrumented. You just have the same binary. You just launch it with tau exec, and then you can see all the interfaces through that. And then we have the tau exec tool, which allows you to preload the tau's DSO, dynamic shared object, into the execution. And how does this work? You build your application, you launch it using srun, MPI run, MPI exec, you specify the number of ranks that it should run on, like this, MPI run. And then with tau, you can just say tau exec -ebs a.out. And then launch paraprof, you can launch the pprof, you can see the execution of the code. Now this sounds very easy, it sounds very good, it sounds too good to be true, right? That you can just take a binary, you can just launch it with tau exec -ebs and show you what that code is doing. Okay, let's try this on our AWS instance and see how it works. Now, I should follow up by saying that if you had GPUs, you can use tau exec to monitor all of their execution as well. You can say tau exec with the -rockum flag, or tau exec with the -level0, or tau exec with kubectl, or OpenCL, or OpenACC, or OMPT, or event-based sampling, or I/O. You just need to point to the right configuration of tau, and we'll get to that. So if you are using OpenMP with MPI, you just say, I want to use the tag of OMPT with MPI. You can have the same tau directory with multiple configurations, one with OpenACC, one with pthread, one with MPI, one without MPI, and so on. And then you can set these environment variables, and we'll see some of these during the course of our class. But just remember that tau can support different measurement options with CUDA, with pthread, with PAPI for hardware performance counters. And if you configure tau multiple times, you get a stub makefile which describes where that application, where that MPI library exists, and the paths to PAPI and so on. If you're using source instrumentation or compiler-based instrumentation, you need to set this tau makefile variable and use one of these compiler scripts to compile your code. What this does is, instead of MPI F90, you will use tau F90.sh and then compile the code if you want to use source instrumentation. And you will find that tau has a number of these stub makefiles. Now on Cetonix, if you say module use that module file and say module load tau, in the architecture lib directory, which is the cray CNL lib, you will see these make files. At the top, you see without MPI, tau with the AOCC compiler. Then there is the AOCC with PAPI and MPI. There is one with cray, one with PAPI. Then there is one with the rock profiler. There are some with rock tracer. So if you wanted to use a configuration like GNU compilers with rock profiler, you could use this tau makefile, and then you'll use the tau exec with the -t flag. And what this -t does is, if you configure tau in different ways, like with PAPI or without PAPI, it creates a makefile and it creates a shared directory where the libtau.so resides. This library, this libtau.so, is preloaded by tau exec. And when you say tau exec with the -t, with the PAPI, MPI, PDT, it will load that libtau.so from that directory. If you use it without the MPI flag, it still understands that by default it's MPI enabled. It will just search for the smallest makefile that matches that, and then it will pick this. If you use -s, then it's a dry run, and it will just show you what it's doing with the LD preload flags. So with this info, let us just look at an example, okay? And let us use the tau exec tool with the event-based sampling. to find out where the application is spending its time on a simple MPI application. Is that okay?